Hello again, everybody, and welcome back to part 3 of the day. Let me pass the slide. Sorry. There we go. Sorry, PowerPoint just playing up. Right. I hope you all had a chance for good lunch. I hope you're back from lunch. Otherwise, I'm talking to myself. But anyway, eat and listen. Eat and listen. So, last session we're going to look at some specifics for concrete structures, steel and non-linear structures, and also sort of speculation as to where structural engineering computing might be going in the future. So concrete, first of all, beams and slabs is a quite typical concrete problem. What's the best way to model them? Well, the answer is it depends on what you want to model, what you want to engineer, what your conceptual model of the structure is, and so on. So, option 1, for example, a steel concrete frame, you can model just the beams. So the beams span by themselves. There's some slab in between, but the slab is represented by the loads. So you use beam loads or area loads, you break down into beam loads and so on. And the slabs and beams are completely independent. The slabs have no effect on the behavior of the beams other than the loading on them. So in that case, leave the slabs out together. You might use a diaphragm in there for stability, but yeah, not necessarily. Okay. Option number 2, you do model the slabs and the beams. So the slabs are there with shell elements, beams as beam elements, and everything is modeled on the centroid. So by default, this is where all the elements are. They're all on the centroid, and the slabs will have some continuity between across the beams, but the beam stiffness will be much higher than the slab stiffness, so they act mostly independently. And the beams, they're modeled as rectangles, you design them as rectangles. Option number 3, again, you've got the slabs and the beams in the model, but this time we offset them. Now in this diagram, I've offset to the centroid of the slab. Reality, maybe it should be the centroid of the combined sections, which is a little bit difficult to calculate because that centroid varies as you go from the beam to the slab and beam again. Anyway, pick a point. So here, like before, you apply load onto the 2D elements, and the beams and slabs are working together, and they're working together compositely. The offsets we looked at earlier, the offsets in the beams will induce axial forces in the beams, but also in the slabs as well. So they will work, the beams will work as T-sections. They must design them as T-sections. So you must make sure you pick up the axial forces in the slabs adjacent to the beams and ensure that those beams are then designed for that. Now, because this is an FE analysis, the effective width of those beams will vary across the span, and which might or might not be in accordance with your effective width theory. It will just follow whatever the maths decides. So the alternative to that is everything back on the centroid again, but this time we use T sections for the beams. And so the beam sections themselves have some slab in there, and we're back to working independently. Now, in this instance, there's a slight over calculation of the self weight. Watch out for that. But we're now looking at T sections where we define the width of those T sections, engineering choice, and we make that work. Another option, we can model the beams just as the bit which sticks down, a stiffener or a rib. So again, the beams and slabs work together, and the beam bit underneath is essentially mostly in tension, very little bending capacity. Of course, the tension, compression, push-pull between the beam and slab will give us bending stiffness. I've not seen this option much, but it is an option. It's an unusual one, a rare one. It might be suitable for your case. And another option, you're modeling ribbon beams. Yeah, you've got very wide, shallow beams on the column lines. For those, I would just model everything in 2D elements. You know, the width of the beam is considerably more than the thickness. 2D elements are appropriate for the within. Now, you'll note in this, everything's on the centroid. I've not modeled either of them offset. Now, reality is there will be a flush top surface, a step in the bottom surface, and there will be a small amount of TL-shaped behavior at the junction, but entering judgment, not much. There might be in your case, in this case, not much, therefore can ignore it. And again, we just make the sections, rectangular sections work and say, well, there's a little bit of facultative flexibility, whatever, between the two. All models are wrong. Some models are useful, and we make the structure work the way we want it to work. Okay, so overall modeling. Now, another option we can do with concrete slabs is, you know, about the ribs, modeling explicit ribs. Now, here's another option. It's a rib slab, but we use implicit ribs. We don't directly model them. So we model flat shell elements, and we model the shell. So see in the diagram there, there's the rib slab. The main top thickness is lowercase t. And we say, right, we're going to use shell elements throughout with that thickness, and that gives us our stiffness in the y direction. But in the x direction, we can't. Now, if we have orthotropic elements, and some programs have orthotropic elements, then you can define the two properties in each direction. If you do not, and you have isotropic elements, but orthotropic materials, then we can use the orthotropic materials, but we need to calculate an orthotropic material stiffness to account for the ribs. And so this gives us some maths. So the Young's modulus in the y direction is our concrete Young's modulus. And the I value is based on the T thickness, CD cubed over 12. C being the nominal width. The nominal width in this case will be this distance between the ribs. We can in the other direction, but we go with C as our nominal width. The area of this section, we're now looking in the other direction. It's the thickness times the width plus the area of the rib. So this is the effective area in the other direction. And then we have this complicated formula for working this value called y. And from this, we can work out an equivalent I value in the x direction. And then from this I value, we know that the equivalent E value is the basic E value of our x I value in the x direction divided by the I value in the y direction. So basically, this is a fiddle factor to multiply the Young's modulus by the increase in stiffness to give us the effective Young's modulus. Reality is it's the I value that's changing, but we can manipulate this and to give us an equivalent E value, because the important thing is not the I or the E, is the EI value, the combined section and material stiffness, to give us the overall stiffness of the section. That's the thing we're looking for. Yeah, the E value is wrong, but in this case, two wrongs carefully chosen can make a right and give us the right orthotropic properties. Obviously, don't worry about copying this down. You'll get a copy of the Debney recording. I presume the slides as well. I'm not sure. But anyway, after the session. Other things, flat slabs. Sometimes called flat plates in some countries. At the point where the slabs and the columns connect, you can get some very unrealistic moments. About the element size, and the smaller the element size, the larger the moments. What we have here at the column slab connection is a singularity. So about metaphors, we have a metaphor of a one-dimensional element, a metaphor of a two-dimensional elements, but at the connection it's really three-dimensional. The metaphor breaks down. Now there are a number of ways of dealing with that. One option is to create a rigid constraint and push the elements out so that they match the edge of the column. So you avoid the really high peak moment directly at the column location, and you get some slight funny moments directly around the edge, which, yeah, may or may not be correct. You can get some quite strange behaviors directly around the column perimeter anyway. But anyway, so we can add in offsets to prevent the slabs actually touching the column. We're stopping the column face, or we can say, actually, the bending moment within the column, it's not real, so we just ignore it. Yeah, the bending moment going actually peaks up here somewhere, but it's not a real value. We just stop the bending moment calculation. We just ignore the bend calculation in this perimeter and go with that value. It's quite an interesting exercise to actually calculate what happens to the bending moments in that zone, and is it really a bending moment if you've got a mass, a three-dimensional structure? Bending moments themselves are a metaphor for opposite compression and tension. Bending moments are not real, but they're a useful lie. Modeling cores and walls. Now, if you're modeling a core, there are three basic ways you can model them. Let's have a look. So you can model a core as a single 1D element chain. So in this case here, we've got a column which has the section property of the core. Where you use this, so details, non-important. We can't really model the openings and that sort of thing, but we're only looking at the overall stiffness. So it's quite good for a stability check. Or a seismic check. So we look at the natural frequencies and stiffness and that sort of thing, overall bending moments and so on the core as a whole. It's also a really good check for more detailed models. We'll see in the next couple of slides. But as I said, openings, it's very difficult to account for openings, and it's very difficult to connect beams and slabs into this arrangement. And if you're replacing the beams and slabs with diaphragms, then it's not so much a problem. But yeah, I think bear in mind. Now there are fiddles you can do for, let's say, look at the openings. We say, well, the openings really go some of the way, but not all the way. So we might have a narrow bit of concrete in between and so on. Narrowing of the wall to give effective properties. Engineering choice. But yeah, it is a really simple, quick check type model that you can do. Good for designs, early concept stage, good for checking models. Level 2, build a 3-dimensional core out of 1-dimensional elements. Beams, essentially. So you do a grillage of beams, and each beam represents. So you can see them. Each beam center line. So you might have a wall element here, and so on, and then join them together. You then have beam elements, perhaps at the lintel levels, and then perhaps a rigid constraint at each slab level, or maybe around the outside, or maybe inside as well. Anyway, this is a good approach for getting overall forces on each wall section. So on each wall section, you will get an axial load, you'll get a shear force, you'll get a bending moment on each stick. There is it was very popular back in the days when 2D elements were rare. Yeah, there's no meshing required. It give you very simple results, overall results. On the other hand, it is very easy to get confused when building these models. And things like openings are difficult, variations in openings are difficult, changes in core as it goes up are difficult. It has advantages and it has disadvantages. And then we have the option of using 2-dimensional elements throughout. So we explicitly model all the core, all the walls, all the lintels, or rather walls with openings, which is another way of thinking about it. And this is good for good detailed analysis. You understand exactly how the stresses flow through the walls, go around the corners, and so on. Now, this is good if you've got a good meshing engine with your software. You've got direct control of the openings, no limitations on the geometry. It can be any sort of crazy shape as desired or required from the architecture and so on. Downside, lots of elements, slower analysis, no abstraction of the results. If you look at the wall here, you'll get a variation in axial load across the wall. There's out of plane bending. In plane, it's all just for forces, and you might want to rationalize the forces back again to give you overall values. But it is an option to look at. Deflection of the concrete is dependent on a lot of things. So one of those is the concrete grade. Stronger concrete has a higher Young's modulus. The duration of the load affects deflection. Short-term loads, small deflection. Long-term loads, you get creep and so on. Reinforcement quantity. How much reinforcement is in there? You can see on these charts here, I've got minimum reinforcement for long-term and short-term loads on a section. And likewise, axial load and bending moment affect the stiffness of the section. So on these graphs, we can see the EI, the stiffness of these concrete sections, and there is the applied moment plot here. I've not included axial load. Axial load will stiffen the sections, a bit like, you get a pile of bricks. Pre-stressing increases stiffness. And you can see for maximum minimum rebar, for as the bending moment increases, the section cracks and then either fails immediately or has a long tail off. And this grey line here is the EI value of the gross concrete, the straightforward concrete rectangle. And you can see for short-term loads, for maximum reinforcements, the gross concrete is pretty similar to the section with the maximum rebar. For long-term loads, the reinforcement makes a significant effect, and the gross concrete is closer to the minimum reinforced section. And again, with change in stiffness, with bending moment and axial load not covered. So the gross concrete section is a good first pass when you don't know what the reinforcement is going to be. But for more accurate deflections, you need to know what is the reinforcement, what is the bending moment to give you the deflection, but the deflections then give you the bending moment, and it is a non-linear, as in is an iterative calculation to get them both to give you the same answers. All right, Yanis, we've got a couple of minutes if any questions have come up on concrete structures.
Yes, there is a question regarding to this last slides about how should we in finite elements, how should we model the cracking of concrete, and should we take into account this stiffness change or just ignore it? What is your recommendation?
So obviously the first model you're looking at, your initial model, you want to work out what the reinforcement should be. And so you're looking at purely at bending moments and shear forces. You can then use that to give you the reinforcement, but the deflection might be based on your gross concrete section, which may well, for that you can get an initial approximation based on the Young's modulus and creep factor. A lot of it is dependent on how detailed you need the deflection to be, because obviously what didn't cover in here was variation on the section side, the tolerances. When they're pouring the concrete on site, the thickness of the slab or beam is dependent on how much concrete they pour in, and so on, and it can be a little bit of a variable. So yeah, definitely if you need to understand the deflections in detail, then you do need to take the reinforcement into account, but also bear in mind the difference in stiffness can also redistribute the moments. So ideally speaking, you have a simple option. You go, the Young's modulus is halved, whatever, it's near enough. Or you can say, well, it's near enough, but more reinforcement will deflect less, conservative. Or you can have your FE program iterating with a crack section analysis program to give you the detailed crack section deflections. Not many programs out there can do that at present.
Okay, regarding the concrete, I think at the moment there is no question. There is some general questions, but that I will ask later.
Okay. All right, so let's press on with steel, timber, and non-linear. Mostly steel and non-linear. So first of all, stability. Now, I presume in Latvia, in the UK, structures tend to be, half of them tend to be concrete, half of them tend to be steel. Unless in most of Europe, concrete tends to be more common. So I've got, but I presume that's the same in Latvia. So I've got a little more detail on steel structures than concrete structures here. So stability of the steel structure tends to be rather than most, but bracing in general. And the slabs on the steel frame, it might be an in situ concrete slab with decking, or it might be precast concrete, which anyway, so we quite often do not model the concrete slabs directly in a steel model, but instead you need to model a diaphragm, so the green plane there, which transfers the stability forces to the stability sections. The wind loads through the slab, through the rigid diaphragm to the bracing. So these frames, they have simple bolted connections, pin ends generally. The slab gives stability, and if you were to model the slabs explicitly with shell elements, that would add stiffness and continuity which might not be there, and and you risk under design of the beams. So quite often you just use a rigid diaphragm, do a fast analysis. Now, watch out, software salespeople, they will tend to do everything as a moment frame because diaphragms add a bit of complication and they just want a quick model. But Preston, can they model a steel frame with pin ends effectively? So what we find out is if we model the slab as a diaphragm, we can leave the slab out of this model, and as I mentioned before, if we're modeling just the stability sections, we're modeling just the bracing and brace bay, do we need all the other beams if we're modeling just stability? If we are doing gravity and stability in the same model, and that can work, then yes, we do. Now, diaphragms have some disadvantages. So the rigid diaphragm, it will stop all differential movements in the constrained direction. Now, the constrained direction, in general, for a floor slab, you want it just in the horizontal direction, not the vertical, so they can deflect vertically separately, but in plane they remain the same. Now, if you have, such as we've got the picture here, trusses supporting the slab, you've got to watch out because the top boom of that slab, top boom of that truss, will be in the rigid diaphragm. There will be zero strain, zero differential movement between the top nodes of the top of the truss, so it will report zero axial force in the truss. And if you are doing that, then the diaphragm may be there for stability. You'll need to calculate the top boom forces independently, separate model, whatever. Watch out for that. Do not go, oh, there's no load in the top boom, I don't need to put any section in there at all. No. Also, default for rigid diaphragms is rigid in all 3 or 6 directions. You want to make sure that does not happen. In plane stiffness only, out of plane flexible. Otherwise, you'll get no deflection under gravity. Steelwork connections. So steelwork connections are often pinned, so they don't transfer moments, but the connections can induce moments. So here we have some connections. I think that was Heathrow Terminal 5. I can't remember. Anyway, you can see that there's these connections. There will be axial load in these connections, and because of the eccentricities, it will induce moments in the supporting members. And if there's moment being induced, then you've got to make sure that is designed for. Now, well, that depends on how you detail the model. If you model everything node to node, everything, you'll then need to add in some moments in separate calculations, or you can build the eccentricity into the connections and actually induce the moments directly. Also, as an aside, you can also detail the connections to avoid the eccentric moments. I mean, this is obviously the Pompidou Center in Paris, ARAP project from 1970s. And the reason for these gabarets is to avoid inducing moments in these columns, keep these columns as slender as possible. What you do then get is shear force here, the cantilever and tie rods at the outside. So the moment becomes this lever arm. Probably not worthwhile doing for all projects, but for the Pompidou Center, it was quite an interesting expression of structural mechanics. So to induce the connection moments, generally you would use an end offset if your software has those, or use rigid links. Now, the actual dimension of the offset, the rigid link, depends a lot on when you're modeling. So if you're modeling the beam might be coming in and it might have an end plate or a bolted thin plate or something like that. And so what should the distance be? Now, if you model the beam to the center line, and the beam is fully loaded with the UDL, then the beam will be a little bit over designed, but the column will be a little bit under designed because there's no moments. Now, the Eurocode says to put, I think, 150 mil offset from the face of the column, about the location of the bolts and everything, which is conservative. That gives you the maximum, or conservative for the column, gives you the maximum moment on the column. But be careful you don't under-design the beam. If the beam span is from here, then there is loading at the end you'll be missing out on. Watch out for that. Do not under-design the beam. Another option is to take the beam to the column face. Program will do this automatically, and that gives sort of a compromise between the two. Now, which one is correct? Should you have just one? Should you have two models? One for the columns, one for the beams, and so on. Also, watch out that I've shown the beam on one side of the column. There could well be beams on both sides of the column. Uniform loading will give no overall. So uniform loading will give you no bending moment in the column, but patch loading, partial loading, will give you some moments. So how you load the model might be significant. Alternatively, say load everything to the center line and then add in some notional moments in a separate calculation. If you're calculating the sections sizes directly in the FE model, watch out for those eccentric moments. Now, bracing, bracing should be modeled to the work points where the centroid of the brace meets either the centroid of the beam or the centroid of the column, depending on the detail. Similarly, if we're modeling trusses, depending on the truss connection and the section sizes, the link might go up or down from the chord center line. So this is obviously the second pass on your truss model when you know what the section sizes are. When you're modeling the beam elements for continuity, you can then calculate the actual additional bending moments that will occur in those elements. Or you can say, well, it will go plastic and yield, and that's also fine, as long as you are explicitly designing for that. Okay. Much about offsets, the usefulness of beam offsets. So here I've got a model of a composite beam. So you can see the one-dimensional steel beam underneath, which I've modeled compositely with the slab on top. So the slab and the beam work together, and we break them both down into the same number of pieces with shared nodes. Slab offset up, beams offset down, and we get most of the bending moments in the beam, but also a lot of axial force in both the beam and the slab. You'll also note that the bending moment in the beam is not very smooth. I mean, the more nodes you have, the smoother this will get. But it's not exact because there is some bending moment transfer between the slab and the beam. So this sort of sawtooth is to be expected. One thing to watch out for as well, if you're modeling like this in an FE model, if you're modeling for vibration, then slab continuity is sort of normal good practice. The strains are low, you will get continuity through the concrete slab when it hogs over the supports. For an ultimate limit state model, where you assume that the slab cracks and carries compression only and has zero continuity with the adjacent bays, this is harder to model. And you may start to get tension in the slab. In fact, you can see there are some tension forces being reported in this model, and it's just a single span. Watch out for slab continuity. It's very difficult to model a full floor plate with everything working compactly and avoiding tension in the slab. You need to have, you know, non-linear orthotropic materials and goodness else. Also, when you're modeling the slab and the beam, the engineering structure model is studs in the profile decking troughs. And also these can slip a bit, they can bend a bit, they get partial interaction between the two. That is difficult to achieve in the FE model. FE model, we have offsets down, offsets up. These offsets are rigid links, and effectively we've got complete stiffness connection between the two. You could model the studs explicitly as spring elements, and that will give you a more accurate result. Would it give you much more accuracy for the effort? Have a go. Do an experiment and see if you like the results. And there might be times when it's needed, might be times when it's not. And we talked about orthotropic materials for rib slabs. We've essentially got a rib slab here, except this is a profile decking. So if now this would be a situation where we're modeling the composite beams for floor vibration. We want to know how the stiffness improves along the beam and in the slab band across between the beams. We can use this approach for calculating the two effective Young's moduli for the orthotropic material of the concrete. And you see it's essentially the same as we looked at for the rib slab. Slightly different calculation, but the end effect is the same. I also will say that about the loading duration for the concrete. See, the Young's modulus for the concrete is actually quite a lot higher than the normal version. So this for vibration will be the dynamic modulus of concrete rather than the short-term modulus. So concrete stiffness under low strain vibration is quite high. Obviously, getting to seismic, it starts breaking and everything, different matter. But yeah, general serviceability of a vibration, quite a high stiffness in the concrete. Mentioned buckling. So if you're doing a buckling analysis, the meshing of the structure can affect things. So if we're looking just a single column buckling, remember the buckling, it's looking for a multiplier of the applied load such that the stiffness, lateral stiffness, goes to 0. Now, if we look at this column with just full length, such as we might do for a static linear analysis, the load factor in this case is coming out to be just over 1,000. Now, if this is a 1 kilonewton node, let's say, okay, it's got a capacity of 1,000 kilonewtons. Now, we add in one mid-height node into this column. The load factor has dropped down to 879. So yeah, it's a 20% reduction in capacity. Fair enough. And if we were to add more nodes into this, we might see a smaller drop, but I would expect for a single column like this, break it in half once, it's probably close enough. You don't get much additional benefit from this. Now, the reason for this drop is because the way that buckling analysis works, it's looking at the translation or rotation of the degrees of freedom, which are the nodes. And in the first option, there's a node at the end, and it's looking what's the rotation on a node, which then induces, which then gives us zero axial stiffness. Now, the second option with the mid-height node is said looking at the translation horizontally of the mid-height node, and that's at the point of interest anyway. That node is a remote from point of interest. So this is a more accurate analysis, and it gives us a lower factor of safety. Now, that's for 1D element. A single mid-height node is usually enough. Experiment. Split it again, see if you get much difference. Now, when you get onto shell structures, such as this cooling tower that I've modeled here, the meshing can have a significant difference. And the general rule is you keep subdividing the elements down until you don't get any significant change in the results. Now, the element size I've got here, I'll talk about degrees. What I mean is the element size, it's a bit easy to see on this one. So a 30-degree element, there are 12 element edges going around the circle. 2.5 degrees, it's 365, there it is, lots more. And we can see in the very crude model on the right, we're getting the deflections, and you can see that the deflected shape is directly following the meshing itself. We see the meshing is driving the buckling shape. This should give alarm bells. The deflected shape on the right side, so this is exactly the same overall geometry, exactly the same load, which in this case was just self-weight. It's giving a deflected buckling shape which doesn't follow the geometry, doesn't follow the meshing, and therefore it's more reliable. And we can see on the graph on the right hand side the buckling load factor against self-weight, in this case to the other loads, and you see for the crude model the buckling load factor is considerably higher than down here at the 5 to 2.5 degree element size. A crude model will seriously underestimate the buckling capacity of a shell structure. Now, things to watch out for. If you look closely, you can see the buckling load factor actually increases slightly for the smaller elements. That's because there's a slight difference in self-weight calculation. If this was external applied loads, it would probably be pretty similar. They are still pretty similar. They're not. It's not a significant difference, but you can see you need to get the model elements small enough. Other thing to note that if in this case we've got a double curved surface, and we just, let's say we start off with this crude model and just split all the elements in half, that won't necessarily help very much, because the real structure is a smooth curve. If we just split these flat elements down, we'll just get larger flat surfaces in more detail. When you're splitting these curved surfaces down, make sure the split results still give you the curved surface, otherwise you'll get localized buckling, flat surfaces, and so on. Speaking of buckling, we can do linear modal buckling and we can do non-linear buckling. So a linear buckling, it's using the eigenvalues, eigenvectors to work out what load factors, what load multipliers, will give us 0 stiffnesses somewhere in the model. Now, if we do a non-linear buckling, this is where we take the structure and we increment the loads with a non-linear solver, possibly with non-linear materials, and we increment the loads up to failure. And if we compare the results, so we can see this dotted line here is the linear buckling capacity, and you see it calculates a single capacity, and the displacement is irrelevant. It doesn't take the displacement of the structure, just the capacity, and when it displays, it will give it a nominal displacement, usually 1 meter. The non-linear analysis, incrementing the loads, you can see the displacement of this node at the center point. It moves slowly, and then suddenly starts to go. And you'll find that this capacity usually approaches but doesn't quite meet the linear capacity. The non-linear will always give you a slightly lower value. And if you use material yielding as well, this will be an even smaller value and possibly, sort of dip down here and so on. Now, if you're doing design, then as a general rule, the buckling load factor should be, if the buckling load factor is 10 times the applied load, the buckling is not giving you a problem. If the buckling load factor is 1, then it is failed. And in between the two, so it's not a factor of safety, it's sort of giving you the same, well, the buckling is affecting the capacity and needs to be taken into account. So buckling load between factor 1 to 10, you need to do additional calculations, more investigation, non-linear buckling, and that sort of thing to find out exactly what's happening. Just because the buckling factor is 2 does not mean you've got a safety factor of 2. That is a misconception. It means it's getting close to failure, but it is affecting it. Sections not they start to go, and then yeah, it is a non-linear relationship once you get into the low buckling values. Obviously, if you've got a buckling value less than 1, it has failed already, and you need to deal with it immediately. So non-linear structures in general. So cables, for example. Well, any non-linear structure, we are finding the equilibrium at the deformed geometry, the deformed position. We are expecting large displacements, and we find the equilibrium at these displaced locations. Now, reality is all structures are non-linear. If you load a big beam up, it will deflect until the stresses build so that the reaction generated by the beam is exactly equal and opposite to the applied beam. It's just that the deflections are very small, so we can say linear is near enough. For these structures where we're getting large deflections, then that's not good enough. So, for example, a cable, you might start off as perfectly straight, but we know that it has no bending capacity, and therefore, under a linear analysis, has 0 resistance. The reality is we know that it does, but it will sag until we've got that V, and then the axial loads will be generated, and it will carry the load. So the factors that will affect this final deflection is the applied load, the cross-sectional area of the cable, the pre-tension that we put into the cable, how stiff the supports. Support stiffness moving in and out will affect the deflection, possibly quite a lot. What's the span? Obviously, the Young's modulus of the material, whether it's yielded or not. And interesting enough, these elements, these cable elements, they could yield but still remain stable, in that they will yield and then just deflect more. and then the ankles change and will take up the load. Also, got the initial sag. How much does it sag initially, and so on. So there's always various factors that make it difficult to calculate the deflection, and this involves quite a lot of non-linear analysis to try and find what that deflection is. It iterates down till you get to a stable situation. Now, on the other hand, if you start out and say, I want the deflection to be this much, you can say, from that position, if you define the deflection first, it's very easy to work out what all the stresses and strains and so on are on the structure. So it becomes quite a linear analysis if you start from a defined deflection. But then you go work out what size of structure, length of cable, and so on you need to generate that in the first place. There's ways and means. So these nonlinear structures. Things to note that the change in the load can change the load path. So here we have a very simple example. It's a braced bay, and the bracing elements are tension only. And on the left we have a load going to the right, and on the right we have a load going to the left. I mean, wind reversal, let's say. And we can see the wind going one direction activates one bracing element, and the wind going the other direction activates the other bracing elements. The load path to the ground and everything changes depending on the load direction. This means that we cannot analyze, let's say, this one on the left and say, oh, wind reversal, we just apply a -1 to the values, all the loads and everything, and it'll give us the right answer. No. A -1 on this would be, it have the ties in compression and so on. It'll be completely wrong. This is why for non-linear elements, we need to analyze the different directions of the loads in different analyses. And for example, here is the, let's get the pronunciation right, Vanshu. I hope that's close enough to the correct pronunciation. So this is a non-linear structure, and we have these cables in tension, and if the loads were to be reversed, let's say you had sufficient wind uplift to put the cable to overcome the self weight of the deck, which could put the cables into, well, compression will buckle the cables and everything. So basically, with these sort of structures, you, as in general, the chance of the wind uplift overcoming the self weight of the deck is slim. But if you were to analyze the wind and the self weight separately, you'd analyze the wind without the self weight, and suddenly the bridge deck would span from support to bank, and that would be nonsense. Reality is, the wind will offset some of the self weight, but that might be combined with, let's say, a large load here, which then causes an uplift here, and so on. You need to analyze explicitly what the load combinations are to see how these sorts of structures react. So second order effects. So, like buckling, when the axial load is high, the linear analysis and non-linear or p-delta analyses can give very different results. So here we have a single column with exactly the same loading on it. In fact, this is the one model. I've run this model with two analyses, one with a linear, one with a non-linear analysis, then just overlay the results. And you can see that the deflection from the non-linear analysis is considerably more than the linear. The horizontal load is quite small, but this is a reasonably slender structure, and so we are getting a p-delta deflection. So looking in detail at this, a linear analysis, remember, equilibrium is at the undeformed configuration geometry. The reaction force F is equal to the applied force P. The shear force is equal to Q, the applied force, and the moment is the Q times the height. Very simple, straightforward calculation. We're doing a non-linear or p-delta analysis. Remember, with equilibrium at the deformed position, and so this force is a factor of the P and the Q values with factored by the angle of deflection. The V, again, horizontal force, horizontal reaction, factor of the Q and P, and the moment is the Q times height again, plus load P times the delta of the deflection. So this is the P delta moment which has been generated by this displacement. Now, what is that displacement? Well, a P delta analysis would do an initial analysis, work out the loads, then do the geometric stiffness, reduce the stiffness of the column, analyze a second time, and it'll give you a single displacement. A non-linear analysis will keep iterating until you get to the final position. And watch out for anything more than a very tiny deflection. The P delta analysis can give you quite strange results. So in general, if you're thinking about doing a P delta, I would go for a non-linear. P delta can give you a check on that, but P delta is a sort of a cheap non-linear analysis. Can help sometimes, but not always. So other second order effects we might have. So here we have a simply supported beam, and we've got a point load in the middle, and we get a bending moment out. All well and good. Now, but there's something not quite right here. So this is a linear analysis. You see, in the readout here, it's saying the deformation magnification is 2.5. So this deformation diagram is being magnified by 2.5 times by the software to give us a sensible looking shape. Now, this is currently deflecting a meter, so a 2.5 deflection is not a meter by 2.5. We're looking at several hundred millimeters deflection here on this beam. That is a lot. That is more than the deflection allowance. Interesting enough, the deflection allowances, tolerances, deflection allowances in the Eurocodes are such that if you keep within them, the structure is usually quite linear. Get beyond them, non-linear effects begin to kick in. So let's also look at the stresses on this beam. So look at the stresses on this beam. The stresses are coming out as 670. That's about twice the yield strength of steel. Now, we know that if this was a steel beam, it would have yielded. This is a linear analysis, but it's giving us results. We're saying, well, this beam cannot carry that load. I know we might use it to calculate a different beam, but as is the stress is saying that something is very wrong. If we're analyzing this beam section, this linear analysis is giving us not wrong, well, wrong results, essentially. The calculations are correct, but the assumptions are not. If we rerun this with a non-linear analysis, we find the results are different. So first of all, so we've run this. First of all, you might notice the deflected shape is now a V shape rather than a curve. You'll note the deformation magnification. So it looks similar, still about a meter in the magnified diagram, but the magnification is about 6.87. Magnification is much larger. This says the deflection is actually considerably smaller than it appears, and that's getting better. We also note that the axial load, there's quite a lot of axial load in this now. And so, yeah, it was acting as a beam, now it's acting as a tie in many respects with a bending moment. Bending moment is pretty much the same, and there's also consequently a large horizontal reaction to balance out the axial loads. So this is the difference between a non-linear and a linear analysis in this situation. So look at that in a bit more detail. Here we have a cable with a point load P on it with a span L. It will deflect down until the loads build and the reactions in the cables give us equilibrium. So we know that the tension in this cable will be, we look at half the load because half goes each side, part 2 plus the horizontal reaction. So it's the vertical components and horizontal components of the reaction, and the horizontal reaction is the length times the applied load by 4 times the displacement. And we could substitute that into there, but the tension is dependent on the displacement is dependent on the tension, and let's say if you're trying to work out what displacement is, it's difficult. If you decide on the displacement, it's a much easier calculation, because you've got to remember that forces don't just create reactions directly. Whether linear or non-linear, forces actually create a deflection. The deflection, and that might be acceleration or so on, but it creates a deflection. That deflection creates a strain. That strain induces the stress, and the stress induces the reaction, and the structure will deflect until there is the reaction to the applied load is equal and opposite to the applied load. Linear analysis, we can usually just go, it's all there. Non-linear, we've got to search and iterate through until we get to that point. Now, this is a more involved analysis, but it does give us the ability to have big span structures. So this is the Humber Bridge from the UK, was at one point the longest span suspension bridge. Okay, lots of ground there, but thing about this structure is that it is flexible. If you were to do a linear structure to span this kilometre or so, it would have to be really, really deep. With this structure, the cables deflect, changing geometry picks up the load and so on, and it is flexible, but it's so long it doesn't matter too much. And if you're over in the middle, you might feel it bouncing around and so on, but that is fine. It's within limits. But yeah, these non-linear structures do enable us to take much larger spans than a linear approach does. Similarly, stadiums. We can have large span stadium roofs. Now this is the London 2012 Olympic Stadium by Bureau Happold. And you see there's a steel frame around the outside, but the roof inside is a tension cable. If I bring up the analysis model, you can see this cable on the inside is like a bicycle wheel. It's sort of held in place by its tension against the tension back. So the roof parts are nearly horizontal, a little bit of downward slope, but not much. But it's essentially a balance between the tension to the cable outside and the tension in the cable pulling it in the opposite direction. And then once you've done that, they can then balance these lighting rigs on top of the cable. Each of those is about 50 tons. And these additionally have a backstay to stop them falling in, and a single cable round to stop them falling out. Very elegant engineering design. The architecture well, that's terrible, but the engineering was very sophisticated. Now we also need to look at sort of more flat surfaces, cable nets, fabrics, and the general rule for these, you need to make sure that you have a double curved surface. So generally, catenaries work in one direction. You have a catenary in the opposite direction as well to make sure it can't move in either direction. And these double curved surfaces usually form a conic or a barrel vault or a hyper. So if we look at one example, let's say this is two cable nets. Both are square, so both got the same plan dimensions, both got similar quantity of material, same level of pre-stress, same both hyperboloid double curved surfaces, both with the same point load in the middle. I mean, this one on the left has slightly more material than the one on the right. The question is, how do they behave? Which one deflects more or less? So you might think this one left with a little bit more material will deflect less, but reality is it deflects considerably more. So same overall geometry, it's the local geometry of the cable net itself makes a big difference to the end result, because each of these cables, being a high par, these are actually straight to begin with. These cables on the right, they start off curved. The curve actually gives a lot of stiffness to the cables and means the end deflection is considerably less. So you need to look at geometry as well as the pre-stresses and everything. On the other hand, as an aside, this is a natural cable net, a spider's web, site fabricated. And curious thing about spider's webs is, an engineer, we might build our cable net with double curvature, give it lots of stiffness. Spiders don't do that. So spiders will build them flat. And the spider, this is deliberate. Not necessarily realize it, but spider webs are built flat, and the flatness makes them flexible, because the purpose of a spider's web is not to support the spider or other load, it is to catch flies. Flies are dynamic, they fly into the net. If the web was very stiff, the flies might actually bounce off without the glue catching them. On the other hand, the spiders build them flat, so they absorb the energy and so catch the fly that way. Likewise, my son is a circus performer, circus performer. He does the human cannonball, and when they land in the net, it needs to be a flatness to begin with some little bit of stress, so it then deflects lots and absorbs the energy. What the end structure is used for depends on its geometry as well. You might want flexibility. I mentioned about pre-stress in these tension structures. You've got to get the pre-tension right. So this is a fabric structure. This is the Marseillais sculpture in the Tate Modern Gallery from a number of years ago. Picture on the left, it's still being put up. The pre-tension isn't entirely there yet, and you'll see that it's wrinkling. The stresses in the fabric are not equal, so you get these wrinkles, Huygens tension fields in the fabric. Once it's fully up, if you've done the geometry, the form finding correctly, the pre-stress correctly, and everything, you'll get a lovely smooth surface. Now, so you need to get the geometry right on these and the pre-tensions and right, and quite often you need form finding methods to find these. Now there are a couple of major form finding methods you can use with your FE analysis. There is the force density method, which wants to set the length of the elements in proportion to the applied load, the force density. Or there's the soap fill method, often used in dynamic relaxation, which finds the geometry where the pretensions are in equilibrium. So soap film, you would say, these are the pretensions I want, find me the geometry. Force density, you say, well, these are the pretensions. Force density will find something much faster, but maybe not quite in equilibrium. So force density tends to be used by architectural form finding models. Soap film, dynamic relaxation tend to be used in engineering form finding models where we need that extra level of detail and accuracy. And at that stage, Yanis, we've got a couple of minutes for some questions, if there are any have come in.
So we have quite many questions, but maybe let me ask some questions that are more related to the second order effects and buckling. So one question is how important is to use semi-rigid connection stiffness for the global static and buckling analysis? How much it's important to do that?
Okay, so it is important if the stiffness of the connection is within certain bounds. If you look in the design codes, they do talk about connection stiffness, and you have simple connections where you assume no stiffness. You have full moment stiffness, full moment connections, which means the same stiffness as the connection, and there's the semi-stiff connections, which you do need to take into account. Now, for things like buckling, as a general rule, buckling, you're looking at ultimate limit state, which means things are possibly moving quite a lot. Now, your average steelwork connection, for example, has approximately 2 to 3 degrees of free movement until they lock up. So a thin plate or an end plate, it can move 2 to 3 degrees, and then it'll take up load and become a continuous connection. Maybe not a very strong one, but definitely a continuous connection. So the general rule for buckling analysis is to say, okay, it's buckling, the connection take up load, we'll just apply full strength, full stiffness connections, fully connected, to do the buckling analysis, and then make sure the structure can withstand that. If you're doing sort of the more detailed forensic, this is where we are. What is the detail capacity? What is the the collapse load and that sort of thing? Then you need to take the stiffness actual stiffness into account. If you're doing design model, you say it's not going to fail, and then you just calculate it. You can probably go away with a simpler model for the original design model, but for the collapse or forensic or accidental damage, you might need to take into account the actual stiffness of the connection in that situation.
Okay, then maybe one more general question. It's related to the practice in UK, but maybe you can more generally answer it. So,
okay.
What are the good practices? What is better way? Should we make like one big model for everything, for all structure, or separate models for one for overall stability, one for some stability of specific part of the structure? What is your comments on that?
Yeah, as I said before, don't try to make one model do everything. Now you can, if you're looking at overall behavior, then quite often many steel frames you might model the one model to look at gravity loads and stability loads, but that might be too complicated, and you might want to say, okay, I'm doing cores with 2D elements and so on. I will take the cores out into a separate model and with just diaphragms and ignore the gravity. It's really in a case-by-case basis. Likewise, you might say, okay, I want an overall model, but for this connection, I want to model this connection in detail to understand it. Let's say you've got a welded connection with stiffener plates and so on. That would definitely be in a separate model. Your main overall model 1D elements, 2D elements. It doesn't deal with connection details. You have that one big model and then maybe lots of small detailed models for the connections. There's no definite rule. It's create as many models as you need to understand how the structure will behave under all the serviceability and ultimate limit state situations that you need to look at.
Okay, thanks. There are additional questions, but I think we should ask that later at the.
Okay. All right. So I'll quickly jump into future structural engineering, and I realize we're a touch behind, so I'll go through these reasonably quickly. Now, the future, as the author William Gibson has said, the future is here. It's just not evenly distributed. So some of these things you might say, hey, we're doing those already. Other things you might go, oh, that's an interesting idea. I really need to get into that. So first one, parametric design. So this is a Rhino CAD model with a Grasshopper visual programming, which is used in this case to generate this hyperbolic shape. With various sliders, you can control the geometry for it. We're finding, certainly in companies like Arup and so on, parametric design is a very important skill set for the graduate engineers. And if you're not doing this already, you probably will be soon. So, parametric design for the fancy structures, but also for simple structures, it enables you to change options and so on, even for simple frames. Vary the spans of the beams in one direction, the other direction, the floor heights, and so on. You can do optioneering. Quickly look at the options you can do to give you the most optimum design at the end. And as an example, this is the real structure which inspired my previous model. This is the Camp Adventure Tower in Denmark. And you see it's a double curved surface, but all comprised of straight columns. The parametric design of the outside surface, that's quite easy. I could do that. The parametric design of the ramp inside, which is a constant slope but varying radius, much more complicated. And yes, so it's a very, very clever design on this. Another parametric design. This is King's Cross Station in London. And see, the design of this is based on a number of circular curves, which were then meshed with the beam elements to give the geometry, and we can see the end result is a very elegant structure. And in steelwork, go to London, check it out. It's a nice structure. Also, you might recognize that this is the structure from the cover of my book. Or another parametric design. Notice the double curved surface. This is the Temple Galaxia by former engineers at the Burning Man Festival. Again, you use parametric designs to generate these forms. It'd be very difficult to create these manually. Another thing which I think is on the horizon, starting to get much more important now, is artificial intelligence and machine learning. Now, early stages for structural engineering, and AI initially quest to model human intelligence, but that aspect has fallen away. Instead, AI now gives us lots of techniques that we might use, maybe for the conceptual design, maybe for other options. So, what is AI in general? So, one of the things is automated search. Route finding, your sat nav, is an AI device, but also you're searching through sort of databases. So the internet, Google is also an AI search, but you might also be searching through design options to find the best answers. AI is natural language processing, and you'll see Siri and Alexa and all these others are using natural language processing to interpret the sounds you make, turn them into word symbols, grammar rules, and everything to then work out the question you're actually asking. Interesting enough to note, the grammar checker in your word processor is an AI application, though it's often forgotten. Automated decision making. This is something which may well come in the future. So AI to encapsulate knowledge and rules, expert systems, for example, to say, well, what should you do in these situations? Now, expert systems have proved tricky because most experts struggle to explain what they would do in every situation, and so on. They're difficult to generalize. So what you might do in this situation might not quite apply to that situation, and so on. Whereas the state search option, you say, well, this state leads to this state, leads to this state, this is more advantage. Now, this is used a lot in gaming. So Deep Blue played chess against Kasparov, beat him because it uses a state search to look a few goes ahead to work out what's the most likely best move to go. Kasparov, on the hand, he said he didn't consider all the possible. The number of moves rapidly becomes astronomical. I can't put numbers here. So the number of moves rapidly becomes sort of I think was it 10 to the first 3 moves of chess is 10 to the 100 power 120 possible moves. Crazy numbers. So Kasparov, I think he's expert. He goes, this is the best move. He just knows because humans don't think in this way. Another area, if I can get this nice to advance, is random forests. Now, so state tree search looks at all the options and builds a tree of options from that. A random forest instead takes a database of what has already happened. So in this case, this example I made for a paper recently, there is some cracking, and there's some things that come from trench fill, some things on different ground conditions, some different contractors, and so on. We can create these state trees from the data we've recorded, and then say, well, how might this affect new cases? Now, these are quite general, very specific. To make these more flexible, less brittle, we might have trimmed copies of these trees, but then have lots of them, a forest of the trees, which are then pruned, and we then say, well, this is my situation. You ask all the pruned trees, what do you think the answer is? And the one which gives the most votes back is probably the right answer. Used a lot in things like medical diagnosis now, and so on. So this is proving quite a powerful machine learning technique. Another even more prevalent machine learning technique is deep learning. So this is neural networks based on approximately the way that human brains work, or brains in general work, with inputs which then trigger outputs which then go to new neurons and brain cells, and you get this cascade of triggering through nerve cells to get find an answer and go, oh, it's a video of a cat or something like that. Now, with deep learning or machine learning, what we do is we might have supervised learning where we say, well, these are a number of training cases. This one's a bee, and this one's a cat, this one's a concrete frame, and everything, whatever it is. And you keep putting the inputs in, and you say if the gives the right outputs, we say great, strengthen that. If it gives the wrong answer, we reduce the values and rerun it, and retrain it, train it until it gives the right answers. This is all pattern recognition. Say in this pattern we do this, in that pattern we do that. Problem is with this for engineering, you need thousands, tens of thousands of design cases to give the right answer. It might have some applications. What does definitely have applications to engineering is optimization. So optimization is an AI search. Well, optimizations are AI applications. You might have state searches to search through design options. You might have, here we've got an evolution topology optimization. It just keeps removing the elements which do least until we get to the final answer. We have genetic algorithms where we have a number of design options. We take the best, we crossbreed them to produce a new generation of options. Or we have this one where we have a particle swarm where we're looking at various points in the design space, which is the range of design options, which then say, well, these are good points, this one, and they keep moving, and they will then hone in on the best answer. Or there's design space off. This is looking at the range of options and how good they are. Now, normally we don't know what shape this is. This is a very simple model, which in the paper in Structural Engineering a few years ago, where we can see that there is a definite geometry which is quite spiky and so on. We were trying to find a peak, and that is tricky. So we need AI applications to find these. AI though, AI is not intelligent. Artificial intelligence is not intelligent. Look at these characters. If we're looking at these tests, these are, looking at, okay, so what categorizes these elements against these ones, and we can say these are large and these are small, these are black, white, these are black. AI can do these ones on the left quite well. AI really struggles with categorizing these ones on the right. This one is trying to it's got to recognize that these dots actually form an enclosure and things are inside or outside. And these ones, where there's a shape on a hatched background, we can recognize the triangles and squares or whatever quite easily. We can ignore the background. AI really struggles to ignore the background. AI does not think in the same way that we do. Likewise, AI will see what's there, but not what's not. So you and I can probably see this white triangle here. AI can't see that. It just sees the individual elements. Image recognition is just pixels. It doesn't, which can derive edges. It can't see these edges because those edges are only implied. Likewise, you can fool an AI. So these two pictures look the same to us, but there are a few significant pixels different, which means it might completely misinterpret what the picture is. So AI is also not aware or conscious. So Deep Blue, AlphaGo, both being the world champions, they had no idea their opponents even existed, or even that they existed. AI consciousness only exists in science fiction. AI tends to not be very robust either. Now, ambiguous data. We can look at this and go, oh, it's a duck, or it's a rabbit, or it's a duck or a rabbit, which oscillates between the two. And we go, oh, that's an optical illusion. That's quite interesting. And AI will go, it is either a duck or it's a rabbit. It can't recognize the ambiguity. And it's difficult to say, well, it's both. Now, AI is vulnerable to bias. The data that you put in gives you the results out. If you put in bad data, you get bad results. For example, image recognition. So if this is a neural network for generating pictures from fuzzy images. If you train it only on pictures of white Europeans, then, well, you can recognize, you might recognize this former president of the United States on the left. Train it only on pictures of white faces, it'll give you a white face at the end. Bias in the training data gives you bad results. Similar engineering, but if you have good training data, then you can get very good results. I mean, these are three photorealistic images produced from paintings, and these are very impressive with good training. Same with engineering. Put good training data into the machine learning, you get good results out. AI possesses no common sense. Now, common sense is, well, everyone has common sense. We have common sense because we live in the real world and we experience everything. For example, these two questions here, sentence 1, sentence 2, they differ by just one word. And so the question then is what was empty, what was full. These are both ambiguous as to what the subject of the sentence is, but we can work it out because we know what fullness and emptiness and so on is going on. We have additional knowledge which is difficult to program in without a lifetime's experience. And AI is not going to rule the world just yet. Yeah, it's not artificial intelligence that worries me. It's artificial stupidity. You know, automatic cars which can't recognize white lorries against a bright sky, or stock trading programs which just go, oh, dripping, drop the lights, dropping, sell everything, and they all do that in chaos and everything. It's not going to happen just yet. In the future, who knows? But in the foreseeable future, our lifetimes, probably not. But where it is going to come useful is a number of the challenges we have as engineers. So carbon neutral, carbon net zero construction. Like it or not, we have a global environmental crisis, and we need to reduce the amount of energy, the amount of carbon dioxide pumped into the atmosphere, the amount of materials we're using for concrete and steel. We're using it all up. We do not have an infinite access to it. We need to work out how to build without impacting on the world as a whole. Now it's tricky. And one of the ways we can do that is to look at the various options. More efficient designs, for example, can take us a long way to this net carbon zero. Obviously not building at all will take us even further, but that might be tricky. So the AI might be used in this. This is a Arab project from China, where you can say, well, if we start off with the basic design, and we can use evolution topology optimization to work out what the ideal bracing is, then maybe use other optimizations and durations to work out the best overall form of the structure, to then give us the final design. But once you've run this optimization, you still then got to do all the usual engineering checks. Is it economic? Is it robust? Does it meet all the client requirements and the code requirements and so on? Optimization can be the starting point, and it can be the polishing of the designs. AI assistance. This is one I'm looking forward to. I want an AI to read my Outlook inbox and say, these are the ones you've got to answer first. Forget those, and you do those ones later. And maybe give suggestions of what it should be. There are already some out there which can arrange appointments for you. There are admin assistants which can, you put a chat message on the website. It might well be an AI bot which gives you an initial answer to try and work out if they're standard answers, or maybe you do need to speak to a human. These are coming. Likewise, engineering assistants on site. You can already have robots or drones which can walk or fly around your site, scan the site as for that day's construction. That point clouds can then be generated into surfaces, which is probably an AI application itself, and recognize what's in there, and then work out quantities and so on. Now, these site assistants will become more and more common on site, but I would not want to send it to a client meeting. Nowhere near ready for that yet. Similarly, sort of digital fabrication and construction. Car industry has been using robots for building cars for many decades. We will see more robotic construction on site, and in the factories, steel fabricators, for example, already using more robotics. But there are some site experiments with robots, like bricklaying and so on. I'd like to see steel erection. I mean, this is a robot 3D printing a bridge which is to go up in Amsterdam and so on. But yeah, this is the way things are moving. So what should we as engineers do now? Yeah, AI and so on. There's a lot of hype and everything, but the main thing is that we as engineers need to work with our computers. The computers are very good at doing some things, calculations, maths, running through thousands and thousands of options, and calculating which one's the best one. We as humans are better at other things, concepts, ideas, creativity, controlling, telling the computer what it should be looking at or not. So Kasparov describes this sort of combination of humans and computers as a centaur. A centaur, mythical creature, which is the best aspects of a human, best aspects of a horse. We, as engineers, need to be centaurs to work with the computers so we can concentrate on the human aspects, the creativity, the understanding, and so on, and let the computer concentrate on what it does best, which is crunch numbers. Yeah, the engineer of the future is a centaur. And at that point, I'll say thank you very much, and I think yes, we can now take questions on that and any other questions that we might have over the session. And I'll jump on this slide just to say, yeah, my new book just coming out this month. It is available from the Institution of Structural Engineers. There's a web link there. It covers a lot of the topics we looked at today in much more detail, and some others which we haven't. And it's already gained some very good reviews, which is comforting. Nice.
Okay, thanks. So I see that at the moment there is no question regarding to this last session about future methods, or let's say advanced design methods, and therefore I think I can start asking that questions which are already previously asked. So let me start with a more general question. So there is a question about can you share your experience with all-in-one finite element models for the whole building?
Sorry, could you repeat that again, please?
Could you share your experience about all-in-one finite element models for the whole building?
All-in-one models.
Yeah.
Well, as I said earlier, if you're looking at overall behavior of the structure, then the complete model of the structure is very efficient. If you're looking at areas of the structure, such as a connection or a floor operation, or do separate models for just those areas. As always, you design the models to give you the answers that you need, and build the models accordingly. There is no one answer. There's no you should always do this or you should always do that. It always depends on a case-by-case basis what model or what models you need to create, and you need to decide on that.
Mm-hmm. Okay, then there is questions regarding this last topics. Could you suggest some form finding software for the cable structures?
Yes. I mean, so the software that I work on with Oasis is GSA. So GSA has a form finding option there where you can do force density and soap film and structural properties, normal properties form finding. That is very successful and is used a lot by engineers like Arup and Bureau Happold and Expedition and so on. There are some sort of architectural level form finding programs for fabrics anyway. For a program called Easy, gives you approximate answers, close enough for an architect. And a lot of people also these days are using Rhino grasshopper models with the Kangaroo plugin, which gives you force density within the model. So yeah, there are various answers. Obviously, speak to me about GSA, and we can arrange for you to have a look at that.
Mm-hmm. Okay, then question regarding to the buckling. What do you think about buckling of columns, of reinforced concrete columns with variable cross section? So probably there are not a classical stress distribution and so on. And what do you recommend? How should we deal with this with finite elements?
Yeah, so if it's a stocky column, probably not going to buckle. Slender columns, I mean, if you've got varying sections, then yeah, you should definitely analyze it to make sure it's not a problem. In general, if your software can do tapered elements, then and the structured tapers, then use tapering elements, you still need to break it down to small pieces. If your software does not do tapering elements, then you'll need to use normal prismatic sections, and you just vary the section according to the average stiffness in each bit. And I'll give you a pretty good approximation to a taper. Obviously, you need to break it down quite a lot. Tests that I've done, one taper needs to be broken down into at least 4 or 5 individual pieces to give you a similar behavior. So yeah, just break it down, vary each section, and then analyze it to make sure it's good. Also, of course, Euler buckling, if you take the conservative approach, take the narrow section, quick Euler buckle calculation gives you approximate answer. You can do the large section, the small section, that will give you the answer will be somewhere in between the two.
Okay, so then there is some specific question regarding to the precast concrete, and would you recommend to set Poisson's ratio to 0 when do structural analysis of precast concrete structures?
Well, the precast concrete, the concrete itself does have a Poisson's ratio. So why would you set it to 0? I mean, if you're dealing with one-dimensional elements, the Poisson's ratio has no effect anyway. If you're dealing with 2D or 3D, then the Poisson's ratio can have an effect. So, yeah, I'm not sure when you would want to set it to 0.
I think there are sometimes in the literature recommendation that when concrete is cracked, then Poisson ratio can be used as 0. So
okay,
probably because of that, there was this question.
Yeah, I must be. I've got far more experience with steel structures than precast concrete. So I'm not a precast concrete expert.
Okay, then there is some questions regarding to the specific slides. So slide number 151.
Oh, okay, just a minute.
About trusses, about steel trusses, and then there's a question: what is a maximum allowed eccentricity in this case when we should not make complex model and insert this rigid link, and we can just ignore it? What is the advice how to deal with that?
Again, there is no definite answer. I mean, on the left, let's say, there will come a point where you might as well have just a short element here, rather than 2 nodes. I mean, as a rule of thumb, I might say if that dimension is twice that one, then maybe you could then go over to having separate elements. Yeah, there's no definite rule, but again, the question of sensitivity analysis. If you know you're in that border area, make the 2 models. Even as an experiment, see which one behaves more appropriately. So yeah, it's engineering's fuzzy. There's no definite answer to any engineering problem. To a formula, it's a definite answer. To engineering, no, there is no one answer. So I would say approximately that is twice the depth. Yeah, you're probably looking at just connecting directly rather than having the rigid link in there. But yeah, the rigid link is an approximation to what's actually happening in the connection anyway.
Okay, then there is one question regarding to the Euro codes, and the question is, do you have any information about progress in Euro code 1993 114, which called design assisted by finite element analysis? Do you have information about that?
Alas, no. I'm not party to that information, but yeah, it does sound interesting.
Okay.
But no.
Okay. So then there is also questions regarding to the pre-stressed hollow core concrete diagrams, and what is your recommendations on simplified and reliable analysis of such structures? How we should do it with finite.
So if you're analyzing the concrete sections themselves, then yeah, I mean you can look at a straightforward just cross-section analysis. We do a program called ADSEC, which does look at concrete cross sections and can do the pre-stress analysis and cracking and so on. Yeah, it all depends on exactly what you're trying to do. So you can look at the cross section to give you the stiffness and the stresses and strains. But if you're looking at the overall behavior, it's you need to then feed that into the other programs to give you the spans and beam slab spanning. Yeah, it all depends on again, it's what question are you asking, and then that will inform what model you need to make.
Of course. So then there is a question which is related to the, as I understand, related to the singularity in analysis. You mentioned about this case when there was a slab on the column, and at that point there is singularity. Yes, but probably you can also give some other examples where it is and how to deal with that.
Yeah, so as I said, these singularities, these occur where in this case, it's where the metaphors of the 2D and the 1D element break down within the column slab connection. This column slab connection is really three-dimensional, but we're modeling it with 1 and 2 dimensional elements. So this analysis works very well when you're away from the column, close to the column. It's strong because the 1D elements, whilst if we display the solids, it looks like there's a section there. Reality is it is just a line with stiffness. So basically, so mathematically speaking, if we reduce these mesh elements down smaller and smaller and smaller, the bending moment will increase further and further and further. And that's come a point where we as engineers will go, no, it's not relevant anymore. The analogy is broken down, and we say no, just stop at this point. So yeah, this is 1 to 2D connections, and also wherever you get sharp changes in direction. Where's my Schleppner model gone to? Yeah, there's that one. Of course, I'm sure I've got a little more detailed one somewhere. Oh, we go. Yeah, so at these corner points, a sharp corner will always give you a stress concentration, and I can't remember the exact formula, but the stress is a function of the radius, or inverse proportion, inverse the radius of of the corner. And as the elements get smaller, the radius effectively becomes smaller as well, which means the stresses increase to a point where, I mean, reality is the concrete will crack at these corners. The stress will be overcome, it will be relieved, the crack will then propagate through, hit the reinforcement, reinforcement takes up the load, should do, and goes from there. So in this situation where you've got these sharp corners, you put the mesh too small, it will give you results which won't be reflected in reality because the stress will be relieved in some way, hopefully in a controlled way, or the stress was relieved in this situation as well in a less desirable way.
I would like to add from my side also that sometimes there is even not like a infinite stress concentration, but simply when you do analysis with, for example, 3D solid finite elements, you sometimes get much higher stress in some places than with simple analytical approach, and then there is a problem that Eurocode usually is designed for a simple analytical calculation, and when you mix it together with this very detailed finite element analysis, and sometimes you cannot design anything. It's always not fulfills in some points.
Yeah, I mean, you have to remember St. Vincent's, I can't remember. Anyway, Saint what's face principle of local effects don't necessarily translate to global effects. So, for example, the situation with point loads on a beam, you might have 1 point load or 2 point loads close together and so on. With the same load in equilibrium, the results for the bending moment as a whole on the beam are the same, but the local effects of the point loads has a huge effect. So if you apply your point load on an actual knife, that will give a very different local behavior to applying that load spread over a smaller area. So the overall behavior will be the same, localized behavior will be quite different, and there comes a point when you don't apply loads by a knife, hopefully, on your structure, but the beam connection does become effectively an area, or the bolt becomes an area, and so on. Yeah, there comes a point when you have to remember that a point load application is not a mathematical point. Reality is there is an area. I mean, the only singularities in nature are black holes, and we don't try to deal with those. There comes a point when yeah, the analogy of the 1D, 2D, whatever, stops, and it becomes sort of masses and areas.
Okay, yes. Then there is results regarding the post-processing of finite element results, and the question is, what is your opinion on preparing finite element models for other engineers to use in post-processing? Is it good idea, or maybe it's better to do like normally, to give just a report?
Yeah, I know this. It depends. So if you are, if the other engineers are within your company, within your design team, then and their job is to review the model, to check the model, to check the results, you've got to give them everything. That they've got to see everything, and they've got to see your assumptions and what you've done and the other results, and that they might want to, oh, what happens if I prod it here and there and everything? Does it still behave correctly? And so on. If the results are going out to some third-party checking engineer, it depends what they ask for. Sometimes you might just give the results. Sometimes they might say, no, we want to see the model itself. It will vary project by project, client by client, location by location, what you need to give. But internally, definitely no hiding nothing. Externally, you might want to filter down to just the significant things, the significant results.
Okay, then there is one question. So, is the nonlinear analysis as a sensitive to mesh size in the corners as a linear elastic analysis, or it's not so sensitive?
It depends. So, if you were analyzing this with a non-linear material which could yield, then it could become less of a problem. I mean, you will get definite yielding down here, but the yielding might not progress that far. Where non-linear models become sensitive to is they're much more sensitive to differences in stiffnesses.
Mm-hmm.
So a linear analysis, you can have some quite large and quite small elements, and it still functions quite well. Non-linear models tend to be much more sensitive to stiffness ranges. So you've got to have models closer together in stiffness. So, for example, doing a non-linear model, I might have some quite large elements, which therefore quite low stiffness, and it gives problems. I subdivide those ones so they give similar stiffness to other parts of the model, and that can improve the analysis convergence. So yeah, in that respect, yeah, the mesh sizing and that sort of thing can affect non-linear performance. The end result should hopefully be the same, but getting to those results should be quicker if you have sensible comparison. I could go into the reason why, but unless we're quite short on time, I don't know how many questions we have left.
Okay, there is I guess at the moment some 3 questions left, and one question is regarding slide 59.
59.
Yes.
Yep.
So the bending moment is the same as for a simply supported beam and no hogging moment because of the spring stiffness. Did it have any effect on lateral torsional buckling in this case?
It might do. I mean, this was just a static analysis. The lateral torsional buckling is really dependent on the restraint. So the average beam is restrained on the top flange, let's say, and so lateral torsion, so the restraints will work for the sagging moments, but not the hogging moments. For example, if you've got a slab on the top of the beam. So in this instance, it might improve lateral torsional buckling behavior if it was analyzed for. I mean, what you don't see in this diagram is just how much this beam is deflecting. It is going down quite a long way to give these results. So I think lateral torsional buckling was not your problem, more serviceability problems of people bumping their heads on the ceiling is be more of a problem for this model, or just sliding down the middle.
Okay, then maybe there is just 2 minutes, maybe some last questions. So could you go to the slide number 122?
Yep. Yep.
Okay, for this type of truss, sometimes at the support there is some eccentricity. This inclined chord is not exactly in the support, but it's like offset, and then there is some this top chord is like a in a very short span, working like a beam. Let's say. And do you recommend to design it as a beam, or to do something differently in that area?
Well, as a general rule, you've got to design for the forces and moments which are there. So if the end bit of the truss is working as a cantilever beam, then you've got to make sure that you design it for the bending moments and shear forces that are there. If you don't, how will the truss behave? Will it still stand if you don't design for the shear and bending, or will it collapse? So yeah, if the forces are there, then you've got to make sure that they are designed for. If the structure yields and it's still stable, then maybe you don't. But yeah, it's a case by case. But chances are yes. Remember the the Florida University bridge collapse was a connection which just wasn't quite strong enough, and one connection failed, and it brought down the whole structure. Likewise, the Hyatt Regency Hotel walkway collapse, again, a connection which wasn't quite strong enough. Killed a lot of people.
Okay, yes. So yes, actually the time is over. There is one more question.
Mm-hmm.
Can I ask it, or we should?
Yeah. I'm okay to continue if you want.
Okay, then there is a question regarding to the nonlinear analysis of reinforced concrete slab, and the question is if we don't know exactly the reinforcement, can we do this analysis with assuming some ratio of reinforcement, and what is your recommendation on that? So if you don't know exactly reinforcement, but you know that approximately there will be some numbers.
Yeah, it's tricky. So if it's early stages, you don't know reinforcement yet, you want to make an approximation. You know from the code what the minimum reinforcement is. You know from the code what the maximum reinforcement is. If you go, well, it's probably halfway between the two, and use that as the starting point. It won't give you the end answer, but it can give you the initial answer. So that's where I might start from, perhaps before, but later on you will know the forces, you will know the reinforcement, and so on. Also, of course, with computers, these sort of things you can iterate. You can do an initial calculation, initial assumption, work out the reinforcements, reanalyze, recheck, and it can just bounce back and forwards between the various algorithms until they both give the same answer, and that's fine. Hand calculations, nightmare. Computer calculations, computers just love doing number crunching, just doing the sums until they're told to stop.
Okay, yes, and I think these questions related to the finite elements are probably over. Yes, I don't see any. Yeah.
Okay. Right. So at that point, quick plug, but I'll say, thank you very, very much for your attention. I hope you found that the session today useful. What I should do is, if you need to contact me, you will find me on LinkedIn. Does my email go out with the information, Yanis? I can't remember.
We will ask them to send it out if possible.
But if it's necessary, you can always pass on questions to me. You'll also find me on LinkedIn. Where's the initial one? Do I have the? There I am. So you can find me on LinkedIn. Email address peter.debney@arup.com. If you've got further questions you want to ask, contact me directly. But Yanis and Yanis can also pass on your Yanis squared, show me the questions if you otherwise.
Okay, a lot of thank yous for the seminar, and we hope to keep in touch with you in the future.
Great,
So
thank you.
thank you very much.
All right.